Welcome to our presentation on normality analysis in SPSS. We will journey from the core theoretical assumptions to practical, hands-on implementation. As highlighted here, understanding normality is truly the key that unlocks the power of parametric statistics. This session is designed to clarify why this assumption is so fundamental and how to properly test for it using a common software package. For instance, imagine you're a financial analyst. Before you can use a standard t-test to compare the returns of two different stocks, you must first ensure that the returns for each stock are normally distributed. This presentation will show you exactly how to verify that. So, why is this concept of a bell curve so important in the first place? Let's explore what happens when reality doesn't fit the theory. In statistical theory, we often idealize data as following a perfect symmetrical Gaussian distribution, famously known as the bell curve. This theoretical normality is the foundation for many powerful parametric tests. However, when we look at real-world economic data, such as loan amounts or the time taken for decisions, the reality is often quite different. This data tends to be highly skewed, not symmetrical, frequently resembling log-normal or Pareto distributions. The conflict arises when we apply parametric models, like t-tests or ANOVA, which inherently assume this perfect symmetry to inherently skewed data. The consequence of ignoring this mismatch is significant. Your statistical power diminishes, and you face a higher risk of committing type 1 or type 2 errors, ultimately rendering your research findings invalid before they even begin. For instance, an investment bank analyzing loan amounts might assume normality, but in reality, there are many small loans and a few very large ones, creating a skewed distribution. Applying a t-test in this scenario would lead to an incorrect assessment of risk. To avoid these critical pitfalls, we need robust methods to test our data's distribution, which brings us to the logic of hypothesis testing. When determining normality, the first step is to ensure your variable is continuous or metric, as these tests are not suitable for categorical data. The choice of which formal test to use primarily depends on your sample size. For smaller samples, generally fewer than 50 observations, the Shapiro-Wilk test is recommended due to its higher power in detecting non-normality. For larger samples, with more than 50 observations, the Kolmogorov-Smirnov test, specifically the Lilliefors corrected version, is the appropriate choice. It is also crucial to check for outliers, often done effectively with box plots. A critical point to remember for very large datasets, exceeding 1,000 observations, is that formal statistical tests can become overly sensitive, flagging minor, practically insignificant deviations as statistically non-normal. In such cases, relying more on visual inspection through plots like histograms and QQ plots provides a more robust assessment of normality. Beyond the basic Shapiro-Wilk and Kolmogorov-Smirnov tests we've discussed, an analyst has a wider arsenal of tools. For univariate normality, you might also encounter the Anderson-Darling and Kramer-von Mises tests, which can be more powerful in specific scenarios. However, for more complex analytical models like structural equation modeling or multivariate analysis of variance, you'll need to assess multivariate normality. This is a much stricter condition, requiring specialized tests like Henze-Zerkler, Mardia's, or Royston's, as univariate tests alone are insufficient. Crucially, statistical tests should always be complemented by visual diagnostics. Histograms provide a quick look at the data's overall shape and symmetry. Box plots help in identifying outliers in the spread of your data. The QQ plot, or quantile-quantile plot, is excellent for directly comparing your data's distribution to a theoretical normal distribution. Combining these visual checks with formal tests gives you a complete picture of your data's normality. When performing a normality test, we begin with a clear hypothesis. The null hypothesis, denoted as HO, assumes that our data does indeed follow a normal distribution. The alternative hypothesis, HA, is what we accept if we find sufficient evidence against the null. It states that the data does not follow a normal distribution. These tests essentially quantify the deviation between our observed data's cumulative distribution and a theoretical normal distribution. If this deviation is substantial, we reject the null hypothesis. This brings us to a critical distinction, the p-value trap in normality testing. Unlike many other statistical tests, where a p-value below 0.05 signifies a desirable, significant result, in normality testing, it's the reverse. A p-value less than 0.05 indicates that your data is significantly different from a normal distribution, often a bad outcome if you need normality for subsequent parametric tests. Therefore, our aim in normality tests is to achieve a non-significant result, meaning a p-value greater than 0.05, which allows us to comfortably assume our data is normal. We've discussed how various statistical tests rely on normality, but it's crucial to understand that not all tests have the same requirements. For fundamental tests like t-tests, ANOVA, and Pearson correlation, a strict normality assumption of your raw data is indeed required. However, linear regression introduces a key nuance that is often misunderstood. A common misconception is that your independent variables, or predictors, need to be normally distributed for linear regression. This is actually not a requirement. The critical assumption for linear regression, which ensures valid inference for your model's coefficients and p-values, is that the model's residuals, the errors or the unexplained variance, are normally distributed. This means you shouldn't obsess over the normality of your predictors. Instead, build your regression model, then generate and check the normality of its residuals, often using tools like a QQ-plot, as illustrated on this slide with good residuals aligning perfectly with the normal distribution. To begin our practical application in SPSS, the most common way to access normality tests is through the Explore command. You'll find this by navigating through the menus. First, click on Analyze, then select Descriptive Statistics, and finally choose Explore. Once the Explore dialog box opens, you will move the continuous metric variable that you want to test for normality into the Dependent List box, as indicated by the arrow on the slide. The reason we choose Explore is that it's an incredibly versatile, all-in-one tool. Unlike the simpler Frequencies command, Explore allows you to obtain a comprehensive set of descriptive statistics, detect outliers through box plots, and generate both normality tests and plots, all within a single procedure. This makes it a powerful starting point for understanding your data's distribution. While the Explore command provides access to the standard Kolmogorov-Smirnov and Shapiro-Wilk normality tests, SPSS also offers an extension path for more advanced analyses. This path, found under Analyze, then Descriptive Statistics, and finally Normality Analysis, requires the installation of a specific extension. The standard SPSS installation typically includes only the KS and Shapiro-Wilk tests. However, installing the Normality Analysis extension unlocks access to more rigorous and specialized tests, such as the Anderson-Darling test, which are often preferred or even required by certain academic journals for their enhanced statistical power in detecting deviations from normality. This allows researchers to meet higher analytical standards when needed. Following our previous step of navigating to the Explore command, the next crucial configuration is within the Plots dialog box. After clicking the Plots button, you will see various options. It is absolutely essential that you locate and check the box labeled Normality Plots with Tests. This is a critical step because if this box remains unchecked, SPSS will not generate the formal normality tests like Shapiro-Wilk or Kolmogorov-Smirnov, nor will it provide the associated p-values that we need for our decision-making. Instead, you'll only receive basic descriptive statistics, which are insufficient for a robust normality assessment. Therefore, always remember to enable this option to ensure you get the full analytical output required for a proper normality check. With this setting configured, we are now ready to generate our results. For our case study, we will be using a dataset called bankloandata.sav. Our goal is to test the normality of the decision latency variable. This variable measures the time in milliseconds it takes for a loan decision to be made. The sample size for this variable is 129. Before we can run the test, we must perform a crucial data preparation step. In the SPSS variable view, we need to ensure that decision latency has its measure level set to scale. Normality tests can only be run on scale variables, not nominal or ordinal ones. If decision latency was incorrectly coded as ordinal, SPSS would not allow you to perform a proper normality test on it. You would first have to go to the Variable View tab and change its measurement type to scale, which is represented by a small ruler icon. With our data prepared and the correct options selected in SPSS, let's examine the output table. After running the analysis, SPSS presents the Tests of Normality table. Given our sample size of 129 observations for decision latency, we primarily focus on the Kolmogorov-Smirnov test results. Looking at the Kolmogorov-Smirnov row, we find the significance level, or p-value, is 0.025. This value is critically important. Since 0.025 is less than our conventional alpha level of 0.05, we have a statistically significant result. This means that the deviation of our decision latency data from a normal distribution is significant. In the context of normality tests, a p-value below 0.05 leads us to reject the null hypothesis. Therefore, our conclusion is clear. The data for decision latency is not normally distributed. We would also observe that the Shapiro-Wilk test, with a p-value of 0.001, corroborates this finding. This necessitates proceeding with caution, potentially considering data transformations or non-parametric alternatives for further analysis. This histogram offers a crucial visual diagnosis of our decision latency data. We can immediately observe that the distribution is far from symmetrical. The data points are largely concentrated towards the left side of the graph, creating a clear peak, while a long, extended tail stretches out towards the right. This characteristic shape indicates what we call a positive skew, often referred to as a right skew. The calculated skewness statistic of 0.618 further quantifies this observation. A perfectly symmetrical distribution would have a skewness of 0. As indicated on the right, a positive value means the tail points right, a negative value means it points left, and 0 means it's symmetrical. This visual evidence from the histogram strongly corroborates our earlier statistical test results, confirming that the decision latency data does not follow a normal distribution. The QQ, or quantile plot, is another crucial visual diagnostic tool for assessing normality. It directly compares the quantiles of your observed data against the quantiles of a perfectly theoretical normal distribution. If your data were perfectly normal, all the data points would align precisely along the straight diagonal line. However, as we can see here, the points form a distinct S-shaped curve, deviating significantly from that ideal line. This curvature is a classic visual indicator of skewness in the data, reinforcing our earlier statistical findings that the distribution is not normal. This visual approach is particularly valuable when working with very large data sets, where formal statistical tests can be overly sensitive and flag even trivial deviations as significant. A clear, systematic deviation like this S-curve serves as a powerful red flag, guiding our next steps in handling non-normal data. When our data does not conform to a normal distribution, we have two primary strategies to consider. Option A is to transform the data. For data sets exhibiting a positive or right skew, which is common in economic data like income, prices, or reaction times, a log transformation is often the standard fix. This can be done in software like SPSS by navigating to Transform, then Compute Variable, and applying the natural logarithm. For example, ln_var equals ln of variable. This helps to compress the long tail